So this video is going to review the three most commonly used coordinate systems and also talk about how you find the integration elements depending on which system you're using. First up, Cartesian. So here's the Cartesian system. The variables here are x, y, and z. And for this one, if you want to do a one-dimensional or path integral, you're going to need to know what is a little step along the path. And usually we use dl for that. Note it as a vector. Direction is important here. So to take a path, maybe you would step a little bit in x, so a little dx step. And it is in the x direction, so we'd put an I hat, the vector there, to signify it. Then a little step in y, like this. There we go, a little step in y, j hat, to signify it's in the y direction. And then maybe we travel upwards in z. So tiny step in z in the k direction or the z direction. Now it seemed like maybe we do 2 dimensions next, but I'm actually going to switch to the volume element, to the 3-dimensional element. And that we usually write with a d tau. So this is volume. And for that, well, we'd be doing like a little box that might look like that. That would be a volume. And this side is going to be a small step in z. This one up here, little step in y. And then this one down here, little step in x. And to get the volume, you'd multiply the length times the height times the width, or it would be dx times dy times dz. Just multiply the 3 sides together to get the volume. We don't necessarily have to write the parentheses. All right, the trickiest one, the 2-dimensional one, where you're looking for the area element. And this one's tricky because it depends on exactly which area or surface you're talking about. So for example, maybe I want to do a surface which looks like that, where I move a little bit of x and a little bit in z. In that case, this area element would be dx, dz, because those are the 2 variables that I'm changing, and it also has a direction, and in this case the direction is always normal to the surface. So here, normal to the surface, that would be pointing out like this or back like that. In either case, that's the y direction. So the direction of this would be j hat. And I ran out a little bit of space there. So we'll just put it right there. That's the j hat direction. Of course, you might also be interested in an area down here in the xy plane, like this. In this case, the area element would be, well, we're moving in x, changing x, so dx, we're changing in y, dy, and then the vector, the normal vector here, would be pointing straight up or straight down, and that's the z direction. So this guy depends on exactly how you're trying to integrate what surface you're doing. So this one you have to actually construct every single time for every single integral. These two, just use these all the time. Volume element for 3D integrals, path for 1D. Maybe you'll get lucky and you won't be walking in one of these directions and you can make that term go to 0. So here we've got the cylindrical coordinate system, and you can see I put it on top of the Cartesian system just so you can get your bearings. The variables here are z, which goes just the same as it does in the cylindrical units. And its range is -infinity to infinity, again, just like cylindrical units. S is kind of like the radius, except for instead of starting from the origin and going up to the point you're interested in this coordinate system, it always starts at the height of your point on the z-axis, and it measures straight out from the z-axis. But its range is 0 out to infinity. And then finally we have phi, and that starts on the positive x-axis and then travels all the way around. So its range is 0 to 2 pi. So these are the variables for the cylindrical coordinates, how they're measured out, and what their ranges are. To set up your integration elements, we'll start with 1D again, getting the path element. And here we might walk on z, so take tiny steps in z. That would be just exactly the same as it is in Cartesian. And then we might take a little step along S, something like that, tiny steps in S. So that would be small step in S, ds, in the S hat direction. And then finally, if we want to take a step in the phi direction, well, we need to take into account how far away we are from the z-axis. So we actually want here as an arc length. So we need to know S to figure out how big our step in the arc length is going to be. So in the phi direction, the tiny length element is S d phi. Now we're going to skip ahead to the three-dimensional or volume element. And notice this one's not a vector. Volume is not a vector, it's just a straight scalar. All right, so if we want to do a cylindrical volume, it would be curvy with phi, go out along S, and then curvy again out here, and then straight up along Z. So kind of as best I can draw it, this is like a chunk of a cylindrical wall or something. So this step here is my S d phi. This side of my element here is dx. This side, that one right there, is ds. So if I want the volume of this red shape, I need to multiply that side by that side by that side. Or ds times dz times s d phi, which if we clean it up a little bit is s ds dz d phi. And you can see how things are really getting messy because we've got variables in our integration limits or in our integration elements. And as before, the two-dimensional surface element, that one totally depends on exactly what surface you're trying to integrate. So for example, say you want to do this top one of the volume element right here. So it's this side times that side, find that area. So that particular area there is going to be this side, which is ds, times this side, which is s d phi. And then the vector, the direction, well, it's normal to this, which is going to be pointing straight up or straight down. So that's z hat. On the other hand, if you wanted to do this area right here, you'd be taking a step, well, it looks like along the x-axis, but it's measured from the z-axis, and that's what s does. So this is ds. This guy right here, that's dz. So this area element, that one right there, would be ds, dz, and the direction, well, that would be normal to this, which is going to be the phi hat direction. So again, for area, you're going to have to look at the specific area that you're trying to integrate over. And finally, we've got the spherical coordinate system. The variables here are theta, measured down from the z-axis, r, measured out from the origin, to say maybe we're interested in this particular point here in this system. So r would be measured out like that, theta down like this, and then finally phi, which is measured in the xy plane and goes all the way around. So the ranges for these variables for r is 0 to infinity. For theta, goes from positive z-axis down to negative z-axis, so 0 to pi, or 180 degrees. And phi, that starts here on the positive x-axis, travels all the way around the plane and comes back. So that is a full circle, so 0 to 2 pi. Now, if you've learned spherical coordinates in math, they actually swap these two variables. These two variables play the opposite role, and that's just an unfortunate historical anomaly. Physics and math just took different paths way back in the beginning, and we're just kind of entrenched now. So keep that in mind, that these two, depending on who your source is, may be switched. Now the integration elements in one dimension for the path integral. Well, we might take a little step in r out like that, and that would just be dr in the r direction, or r hat. We might take a tiny step in theta, but this is, again, it's going to be an arc length that depends on how far out we are in r. So have a smaller step in close, a larger step out farther away. So this little step is going to be r times d theta. And that would be in the theta hat direction. And then we have another arc length when we take a step in phi. And this one depends both on r, but also on theta. Because if we do, for example, a little circle over here, that's a much smaller circle than the same 2 pi radians walk would be if we were down here kind of in the equator zone, if you're thinking of it as an actual sphere. You can walk all the way around the circle in a much smaller length than you can here. So this one is going to depend on r, but also on theta. And it depends like the sine of theta. So the last length element here is r sine theta d phi, and that's in the phi hat direction, and this is the length element for that. That guy is the length element for theta. Now in 3D, we can do a similar thing that we did in the other two coordinate systems. If we want a volume here, which, let's see if I could draw it, it would look something like sort of a bit curvy here as it goes with phi, a bit curvy there as it curves with theta. So here's sort of the back of my element, and then it would go out in r, curve down like that, out in r, curve around like this, up and over. So it would be sort of curvy on two sides, and each of these side lengths would be going with their element. So this one down here that walks around in phi would be r sine theta d phi. This one here would be r d theta, and then this guy here would be dr. So the volume element is going to be this, dr times that, r d theta times this guy, r sine theta d phi. And if we clean this up, gather both of these r's together at the beginning, be r squared sine theta dr d theta d phi, and that's our volume element. As with the other two systems in 2 dimensions, your area element is gonna depend on exactly which area you're talking about. So if we did this front plate here, this guy, we're changing a little bit in phi, we're changing a little bit in theta. So this area would be this guy, r sine theta d phi, times this guy, r d theta, or if we simplify it, r squared sine theta d theta d phi, and the direction, well, it's going to be normal to this like it always is for an area vector, and it would be coming out, and that's going to be the r hat direction. So that's one, and you do a similar thing if you were doing any other. Maybe we do an arc over here, where we're doing an arc in theta, so this would be r. D theta would be that side of the area. We'd stretch out on the radius, so we'd get kind of this fan shape. This would be dr, and then the area element here would be this side times that side, dr, r, d theta, or rewriting that a little neater. R, d theta, dr, and the direction, well, normal to this would be phi hat. So again, for the area elements, as ever, you're just going to have to look and see exactly what surface are you talking about. And those are the coordinate systems.